The National Map is a collection of mapping products and services produced by the USGS National Geospatial Program. These products and services are accessible online at the National Geospatial Program website at usgs.gov/ngp. The National Geospatial Program has released a series of how-to videos for people who are working with the National Map data and services. The videos show how to use the services and interfaces to access data and tools for viewing, analyzing, and printing geospatial data. Lessons 1 and 2 serve as an introduction to the training materials, and the remaining how-to videos may be viewed as needed in any order depending on the user. Any use of trade, product, or firm names is for descriptive purposes only and does not imply endorsement by the U.S. government. Lesson 10J1: Importing and Visualizing 3D Point Cloud Data with QGIS. This lesson will show how to use QGIS, a free and open source software for GIS, to import and visualize point cloud data. The source for the Lidar data used in this tutorial is from the USGS 3D Elevation Program, or 3DEP. The goal of 3DEP is to complete acquisition of nationwide Lidar, IFSAR in Alaska, to provide the first ever national baseline of consistent high-resolution topographic elevation data. 3DEP Lidar point clouds and digital elevation models at various horizontal resolutions are available to the public at no cost on the National Map and Lidar Explorer. By the end of this lesson, you will learn how to initialize QGIS on your machine, an overview of QGIS, how to manage plugins, how to import and filter 3DEP point cloud data, and explore 2D and 3D visualization of the data. For this lesson, we will be using a dataset from El Paso County, Colorado. If you have not done so already, please download the CO_El Paso_County_2018_training_data.zip file from our Rocky Web website at rockyweb.usgs.gov/training_data. This may take a few minutes to download. If you already downloaded this data to complete Lesson 10G1, Importing and Visualizing Elevation Data Using GrassGIS, you can use that folder. After you've downloaded the Lidar data, extract the zip file into a folder on your local computer to use during the lesson. The National Map has a download client where you can find USGS products, including elevation data such as Lidar point clouds, at apps.nationalmap.gov/downloader. If you are interested in learning more about downloading products on the National Map, be sure to check out our training videos located at usgs.gov/ngpvideos. QGIS is a widely used free and open source software for geospatial applications, or FOSS4G, under the GNU General Public License. It meets Open Geospatial Consortium (OGC) standards and can act as a graphical user interface for other FOSS4G software like GrassGIS and Geospatial Data Abstraction Library (GDAL). QGIS supports Entwine Point Tile (EPT), Cloud Optimized Point Cloud (COPC), and LAS/LAZ data formats. When loading an LAS/LAZ tile, it will be saved in COPC format that stores files in a common folder, is indexed, and allows reduced loading time. In this lesson, we will be using QGIS version 3.28 LTR. If you do not have QGIS already installed on your computer, you can download it at qgis.org/en/site/forusers/download.html. Any version newer than 3.28 will work for this tutorial. However, the long-term release will be the most stable, and there may be interface and layout differences. QGIS provides a user manual at qgis.org/en/docs/index.html. Open QGIS. The initial screen may contain recent projects, project templates, and the processing toolbox. The processing toolbox contains numerous geospatial analysis tools, visualization tools, and tools that act as a graphical user interface with other programs. The browser window accesses and allows navigation of your file system, database, web map service and web feature service connections, and XYZ tiles such as OpenStreetMap. Let's add the Layers window, which lists and allows management of imported geospatial data. Click View, then Panels, and select the Layers panel. Beginning with the 3.18 release in February 2021, point clouds can be imported and visualized directly in QGIS. Open-source point cloud processing tools such as Cloud Compare, GrassGIS, or a command line option such as Point Data Abstraction Library, PDAL, allows options to edit point clouds and will be integrated in future versions of QGIS. For tutorial videos on GrassGIS and PDAL, please see the videos 10G1 and 10H1 respectively. Additional plugins can be installed for increased capability, and the profile tool will need to be installed. Click on Plugins and choose Manage and Install Plugins. Click the Installed button on the left side of the window to view the plugins that are already installed. Choose the All tab and search for Profile Tool. Take a moment to read the description of the tool and take note of the latest update. If your results show a checkbox next to the tool, the plugin has already been installed. Click Install Plugin. A notification should appear at the top of the window stating it was successful, and the option to uninstall the plugin will also appear. Close the window. We will import one of the last tiles with the Data Source Manager. Open the Data Source Manager, and in the left column choose Point Cloud. Since this data is saved to our local machine, ensure the source type is set to File. To set our data source, click the ellipses button to browse to our source file location and open the last folder. Select LD 31741380.las. Click Open, and that will populate the source location of the data. Click Add, and as the tile loads, close the Manager window. Save the project by clicking Project, then Save As. Navigate to your directory and name the project garden_of_the_gods. You can easily zoom to the active layer by right-clicking the layer and selecting Zoom to Layer. Unselect all classifications by right-clicking one of the classes and click Hide All Items. To visualize points that represent vegetation, buildings, and cars, select Unclassified by checking the box next to that class. Turn on Ground, which represents bare earth classified points, and explore the tile to visualize vegetation, man-made objects such as cars in this parking lot, or bare ground including roads. Unselect Ground and turn on Low Point Noise. This classification is unknown, but since many of these points surround vertical rock outcrops, it can be assumed that these laser pulses are multipath returns. They bounced between objects and took longer to return to the sensor than the surrounding unclassified points, resulting in the low point noise classification. Turn off the unclassified and low point noise and select high noise. Click the Identify Features button and select the visible point. In the Identify Results window, attributes of this point are shown. This high noise point has a z-value or elevation of nearly 6,900 feet, and could be one of many objects, including a bird. Clear the result and select Pan Map to freely navigate the tile. turn on all classifications by right-clicking on Unclassified and selecting Show All Items, and zoom back to the full extent of the tile. Tile information, statistics, and 2D/3D visualization options are accessed by right-clicking the layer and selecting Properties, or by double-clicking the layer. Explore the different tabs on the left. Information will present an overview of the layer, including coordinate reference system, metadata, and the attributes within this dataset. Within the metadata section, you can see that this tile used version 1.4, which is the American Society for Photogrammetry and Remote Sensing (ASPRS) LAS classification schema. Choosing the Statistics tab gives you an overview of attributes and distribution of your point cloud, along with the minimum and maximum z-value, which is also your elevation. Close the Properties window. The low and high point noise is an outlier classification and may affect visualization or analysis. Within the Layers window, it is possible to turn off visualization for different classifications, but what if we want to filter specific variables? Knowing the geography of a region can help determine accurate point data. Garden of the Gods elevation is approximately 6,400 feet, not including the rock outcrops, and so a minimum z-value of 5,504 feet is likely not accurate. Right-click the layer and choose Filter. In the Fields window, double-click Z to start a script expression, followed by the less than or equal to operator, and put 6,400 as your limit. Click Test to see the points that fit your expression, and if successful, a pop-up should appear. Click OK and keep the query builder open. There are numerous ground and unclassified points on the outer extent, along with several low and/or high noise points. Continue the filter expression to visualize only low point noise by adding the AND operator. Then adding classification is equal to 7 low point noise. Test this expression. Press OK to acknowledge the result, and once more to exit the query builder. Select the Identify Features button to determine the attributes of these low noise points. Click and drag a polygon around all the points within your layer's extent. There are 4 points visible, but 5 points have been selected. Each point's attribute and spatial data is listed, and when selecting any attribute of a point, QGIS will highlight that point in the map window. The second of the 5 points has a z-value of 5,504 feet, and the other points are just shy of 6,000 feet. Reopen the query builder by selecting the filter icon. Select Clear, and your tile returns to showing all points. Click OK to close the window and clear the Identify results. Symbology is an important consideration when it comes to visual representation of data. Visualization of different classifications, like our current tile, can help us understand discrete data, such as differentiating a car from a tree. However, this representation is not conducive for continuous data like elevation. Return to Layer Properties and select Symbology. In the top drop-down menu, select Attribute by Ramp, and for Attribute, select Intensity. Keep the minimum 464 and change the max to 10,000. Click on the drop-down Color Ramp menu and choose Grays. Click on Apply and then OK. Zoom back into the parking lot to better visualize the vehicles and parking lot boundary. Afterward, zoom out to view the entire tile. QGIS supports 3D visualization of point cloud data and is a great way to explore an area of interest. Open the layer properties and choose 3D View. The drop-down by default has Follow 2D Symbology selected. Select Render as a Surface, Triangulate, which will interpolate the gaps between data points and create a continuous surface. Open the Elevation tab and note what options are available. Click Apply and OK. Open a new 3D map view by going to View, 3D Map View and selecting New 3D Map View. Resize the new 3D window if needed, or dock the window into the main user interface. If the screen is blank, click Zoom Full, and then with the mouse wheel or by toggling on-screen navigation, zoom out until your data appears. Hold down the Shift key and click and hold down the left mouse button in the middle of the image. By moving the mouse left and right, you rotate the image on the axis where you clicked. Move the mouse up and down, and the image rotates to view the topography of this area. Open the 3D configuration menu and explore the different visualization options available in QGIS. Click Cancel to exit the configuration window. Changing the symbology from intensity to elevation will affect the 2D and 3D maps. Open the Layer Property Symbology tab. Keep Attribute by Ramp, but change the attribute to be visualized to Z. Earlier, we discovered that the tile's minimum elevation was incorrect. Click on Load to enable the current minimum and maximum Z value, then manually change the minimum Z value to 6,350, and change the max value to 7,000. Choose a color ramp. In this exercise, the Turbo color ramp is selected. Leave the mode as continuous. Occasionally, the symbology may not categorize your data appropriately, and may require adjusting the settings. For example, here we switch the mode to equal interval and then back to continuous to have more than 2 classifications. This will not alter the data itself, but does significantly affect the color ramp and visualization. Press Apply and OK. Since we set 3D symbology to follow 2D symbology, both map windows should reflect the proper symbology. Move around the 3D scene by left-clicking or using your mouse wheel until you have a nice view. It is easy to capture a 3D image. Click on Save as Image and navigate to the directory where you saved the project. Name the image Garden of the Gods and keep the default file type .png and click on Save. Close the 3D map window. A feature within QGIS to visualize change in elevation across distance is the Elevation Profile tool. Open this feature by going to View and selecting Elevation Profile. Select Capture Curve and use the crosshair to draw your line of interest. Single-click the left mouse button to start your profile, and left-click to insert vertices along your path and change in direction. Once your path is complete, end the segment and then single-click the right mouse button to complete your path. While this point cloud data is rendered as a continuous surface, the profile displays the point data. The path drawn here is a walking path from the parking lot around the large outcrop, and shows the distance and elevation change in feet. Click the broom icon if you wish to clear that profile. Save your project and close QGIS. In this video, we learned how to start QGIS on your machine, an overview of QGIS, explored additional plugins, imported and filtered 3D point cloud data, and visualized this data in 2D and 3D. As QGIS continues to be developed, more point cloud functionality will be available. If you are interested in learning more about using various GIS software to explore and analyze data from the national map, please see additional USGS training videos at usgs.gov/ngp videos.